11.3 part 2 is really just more of the same, looking at doing this substitution again and again. When you have trig, it is typically the inner function. This particular question, I don't really think belongs in here. We told you, the integral of sine kx is negative 1 over k cos kx. And you could certainly use that, but I'd like to show you that if I did make u equal to the inner expression for x, then du is equal to 4 times dx. And if nothing else, this is helpful to show that if I just make this substitution, what I would have is the integral of the sine of u, and I can't put dx there, but I don't have a 4. So it's really important that you feel comfortable manipulating the du dx relationship, and I am going to write that as 1/4 du is equal to dx, and this I can substitute. So I'm going to multiply that by 1/4 du. But our constant of integration rule means that I can take that constant out. So I'm going to rewrite this as 1/4 times the integral of the sine of u du, and this is equal to 1/4 times the negative cos u plus a constant. Well, I could distribute that 1/4 on. I get negative 1/4 cos u plus c, but u is 4x, so negative 1/4 times the cos of 4x plus that constant. Now, you had that formula already, but it's nice to see that it works through this substitution rule process. All right, some of them can get a little bit difficult, right? This looks like a pretty gnarly function. And again, it is tempting to say that, x is u. Do not make that mistake. I don't think I've ever seen a question where it's beneficial to make x equal to u, because that's just such a direct substitution that it doesn't simplify anything. So within this expression, we have 2 plus sine x inside of a bracket, raised to the power of 10, multiplied by cos x. I really think, as a general rule, if something is raised to a power, the inside should become your u substitution. So I'm going to say that u is equal to 2 plus sine x, which means that du, derivative of 2 is 0, derivative of sine x is cos x, and I'm include that dx piece. Now that makes this a pretty nice and straight up substitution, because this is going to become the integral of, instead of 2 plus sine x, it's u to the power of 10. Instead of cos x dx, it's du. Well, this is just our anti-power law, so this is going to be equal to 1 over 11 times u to the power of 11 plus a constant, but it is not u. We have to substitute at the end, and we get 1 over 11 times 2 plus sine x to the power of 11 plus some constant. So many students will, crush the substitution rule, but they'll forget this constant of integration. It needs to be there, and in most questions, it's worth, half a mark, depending on what the total question is out of. That constant is a really, really important concept, which we talked about in great detail in Chapter 10. Now, you've probably noticed, I hope, that every problem so far has been an indefinite integral. Well, what happens if it's a definite integral? And the reality is there's only a slight change we need to make. If we make u equal to g of x, then when I rewrite my integral, what I need to do is I need to rewrite those constants of integrations. And I'd like to show you just a simple one. Let's say I was taking the integral from, let's just go 2 to 0 of x squared dx. Well, what if I made x squared equal to, well, I guess I can't do that. Let's say I made, we'll go with that, x squared. Now I have to change my function. Hold on. We'll get there. So I'm going to write this as bracket, maybe x squared plus 1 squared times 2x dx, just so the substitution is nice and easy. So if I make u equal to x squared plus 1, that means that du is equal to 2x dx. So I could rewrite the inside of that integral as u squared times du. The problem, though, is u 0 when x is 0, and it's not. And essentially what I've done here is this step right here is making u equal to g of x. So instead of 2, what I'm going to put is I'm going to put u is equal to an unknown when x is equal to 2. And the same idea, u is equal to an unknown when x is equal to 0. If only we had some way of identifying those values, and we do. It's this. This tells us the relationship between u and x. So when x is equal to 2, u is equal to 2 squared plus 1, u is equal to 5. When x is equal to 0, u is equal to 0 squared plus 1, so u is equal to 1. And that allows me to make this, with my u substitution, a 5 for my upper bound and a 1 for my lower bound. Now, you have another option here. if you substitute the x expression back in for u, you can use the original upper and lower bound. And I think I'm going to make this question a little bit lengthy because I am going to do both. I want you to see that it works. So we're going to move right away to this example. And again, the photocopying is a little bit bad here. The upper limit is 9, the lower limit is 1. We have e to the power of root x over root x, and then a dx there. Now, if you have Euler's number, whatever is in the exponent tends to be the substitution. So I'm going to say that u is equal to, and I'll write it as root x, which means that du is equal to 1/2 times x to the negative 1/2. Or I can write du, I forgot the dx, sorry, can be written as 1 over 2 root x dx. I do not have a 2 in my original expression. If I multiply that over, I can say that 2 du is equal to 1 over root x dx. And the reason that I have to do that is with these concepts or these expressions, I can rewrite my integral. I'm going to leave the upper and lower bound off for now. I'm going to say that this is the integral of e to the power of u, and then this entire 1 over root x dx becomes 2 du. Now, I really want to reemphasize that I can no longer take that integral from 9 to 1, because when x is equal to 9, u is not equal to 9. And the way that we find that is with this expression right here. Now this, if we want to, we can write this as u is equal to g of x. So what I want to know, and I'm going to put up here that my upper bound is now whatever function g is evaluated at 9, and whatever function g is evaluated at 1. Now I don't particularly like to put function notation inside my integral, so knowing that g of x is equal to, what was it, just root x, right? I can say that g of 9 is the square root of 9, which is 3. I could also show that g of 1 is the square root of 1, which is equal to 1. Now what that allows me to do is to come up with the idea, and I'm going to write all this stuff out. I know it can feel a little tedious, but we have now said that the integral from 9 to 1 of e to the power of root x over root x dx can be written as the integral from 3 to 1 of e to the power of u times 2 du. And at this point, we can start to make, we can start to do the antiderivative. So if I take the antiderivative of this red expression, what I get is I'm going to put the 2 out front, and then I get 2 times e to the u plus a constant. And this is going to be evaluated from 3 to 1. Now, I really want to reemphasize that we don't have to use that function. What I could do is I can make my substitution again, and I could say that this is 2 times e to the power of root x plus a constant. But when it's in terms of x, I have to evaluate it from 9 to 1. When it's in terms of u, I have to evaluate it from 3 to 1. Personally, I like the black technique. All right, once you do a lot of indefinite integrals with the substitution rule, you typically become pretty used to doing it that way, and you make your substitution at the end. And at least that way, you don't have to do this extra work right here, identifying, the value of u when x is 9 or the value of u when x is 1. But I really want to show that it doesn't matter. All right, I'm going to do both of these. So my first definite integral is going to be 2 times e to the power of the square root of 9 plus some constant minus 2 times e to the power of the square root of 1 plus that same constant. Well, this is going to be 2e cubed plus c minus 2e to the power of 1 plus c. Not plus c. The negative needs to distribute. So this is negative c. That means my constants will cancel, and I end up with 2e cubed minus 2e. I could write that as 2e times e squared minus 1. Those are the same things, right? I would take either of those, though. Now let's see what we get when we do the red equation. Now I am saying they're equal, so I want to check that. The red definite integral piece here is going to be 2 times e cubed plus a constant, because u equals 3 is our upper bound, minus 2 times e to the power of 1 plus a constant. And I'm sure you're probably seeing at this point that these are the same thing. And it's really important that when x is 9, due to the substitution we made, u is 3. So we're not really doing anything different here. But I think it's nice to see both techniques, because you will get the same thing. I get 2e cubed plus a constant minus 2e to the power of 1 minus that same constant. The constants cancel. If I have 2e cubed minus 2e, I can factor a 2e out, and I'm left with e squared minus 1. both of these gave me the same answer. And it is totally up to you which technique of the, the red or the black here that you want to use, because they give you the exact same answer. Again, personally, I prefer, the one in black, but definitely with very, very complex substitutions, this red technique can be pretty beneficial. All right, definitely a bit of a harder assignment. Substitution rule is tricky. Anytime we need to use an advanced integration technique, it can take a little bit of time and a little bit of space, but it's something that we have to get used to, because not everything is just using the power rule to take the derivative. So not everything is just using the anti-power rule to take that antiderivative. All right, make sure you try those questions. They're up on the board there. As always, email if you have any questions, and I will help you as much as I can.